So section 3.7 is a word problem section. I do most of these problems from this section in my brief calculus class. Technically, they need calculus to solve them, but we can use some algebra skills and possibly some graphing skills to kind of work around the calculus that's really necessary. So these are important problems specifically because if you take a regular calculus class or a brief calculus class, you might see duplicates of these problems. So I'm going to do just a handful of problems. It's a short section, but each of the problems is going to take some time. I don't think I have a twin to number one. My number two is a little bit different, so I thought I would start with doing number one with you just to get us warmed up. So first I'm going to read through the problem, try to understand what's given to me, what's required, and what my goal is. So in problem one, it talks about a campground owner having 800 meters of fencing, and he's going to enclose a rectangular field. I'm going to make W the width of the field and L the length of the field. I probably should write that too. Follow these steps to find the dimensions of the field that will yield the largest area. So let me just make a sketch. So this campground owner is going to build 4 sides of fencing to enclose an area for whatever reason. Maybe to keep bears out or something, for whatever reason. And he has 800 meters of fencing. He's going to be required to use all 800 meters. Of fencing. And the goal is going to be to get the maximum area possible with that 800 meters of fencing, or to enclose the maximum area. Let me just draw a diagram and try to explain to you what's going on. So my rectangle has 4 sides. The sides that I draw vertically, I usually draw them shorter, and I label them as width. The width of the rectangle, and I give them the letter W normally. The sides that I draw horizontally, I call the length of my rectangle. And label those L. So a rectangle has 2 lengths and 2 widths. Question A is going to relate to this diagram and my requirement of using all 800 meters of fencing. I need to come up with an equation for the length of the field, and the length of the, I guess it is a rectangular field that we're enclosing. I need to come up with an equation for the length, which means I need a problem with an equal sign, and the L, the length, needs to be isolated. This isn't particularly hard to do. What the campground owner is going to do, he's building 2 widths and 2 lengths, and between those 2 widths and 2 lengths, they're going to use all 800 meters of fencing. So as I go to do part A, to come up with my equation, an equation is a problem with an equal sign that's solved for length, the campground owner's building 2 lengths and 2 widths, and he needs to make that use up all 800 meters of fencing. That's the requirement. I'm going to use all 800 meters of fencing, building the 4 sides, the 2 lengths and the 2 widths. Part A implies I need to solve this for L. So I'm going to minus 2W from both sides and get 2L equals minus 2W plus 800. And now I'm going to divide everything by 2 and get L equals negative W. I can make it negative 1W, it might help, plus 400. So my answer to part A an equation that represents the length of this field, the field that's being enclosed with two widths and two lengths using 800 meters of fencing, is the length is negative 1W plus 400. Now I'm going to move on to part B. I need an equation for the area of the field. So my answer to part B is going to be similar to my answer to part A in that I'm writing an equation, a problem that has an equal sign. In part A, I wanted the equation solved for length. In part B, I want the equation solved for area. So in part B, I'm going to use the formula that area, which I'm going to use as A, of a rectangle is its length times its width. And what I'm going to do before I write an answer to part B is I'm going to do a substitution. I'm going to take the L in the area equation and change it to negative 1W plus 400. That's kind of why we do part A. So I'm going to get the area is negative 1W plus 400 times W. And I'm going to clear this parentheses by going negative 1W times W and 400 times W. And that's going to give me negative 1W squared plus 400W. So I met I created my requirement. My requirement is to use all 800 meters of fencing building the four sides. And now I have a goal equation. So I came up with a required equation, and this is my goal. My goal is to get the maximum area possible with this equation. Let me show you visually how I can get an answer, and then I'll show you algebraically how to get the answer. So visually, I'm going to sketch a graph of this on my nice graphing calculator. And I'm going to have to do some serious playing with the window because the numbers are way bigger than negative 10 to 10. In fact, I'm going to graph this equation in y1. So in y1, I'm going to graph the equation. I can't do w's on my calculator, so I'm going to graph negative 1x squared plus 400x. And the x's are the widths of this field that we're enclosing. And I know I can't enclose less than 0. My width has to be at least 0. I can't have negative widths. They don't make sense. And I know I can't have more than, a width can't be more than 800 meters because I only have 800 meters of fencing. But I'm building two widths, and if one width is 400 meters and the other width is 400 meters, I'd use all 800 meters of fencing up. So I'm going to make my x mins and x maxes 0 to 400, and these represent the different widths of the rectangular region that I'm enclosing. The y's, because the area is written to the left of the equal sign, that's the area that's going to be enclosed. And here, I'm not going to be sure of what's going on. I know my area can't be less than 0, but I kind of don't know what my y max should be. And I'm going to have to play, but it's going to be a big number. Eventually, I'm going to do these problems without graphing, so I'm not going to have to play with a window. But for one problem, I'm going to show you how you can visualize the answer, just because I think it's kind of important. And this is going to be a big number. I don't know if this was 200 and this was, if all the four sides were, well, let's just pretend like if the width was 100 and this width was 100. That would be 200 meters of fencing. I'm asked to use 800 meters of fencing. My four sides have to add up to 800 meters. So the kinds of numbers that the lengths and the widths can be are in the hundreds. If the widths were 100, I'd have 200 meters of fencing. That would force the lengths to be 300. And the kind of numbers I might get for my area, if I did 100 times 300, is like in the thousands. So the area of a 100 by 300 feet rectangle is 30,000. Let me just guess and put a gigantic number here for my y max. I'm going to graph this function, set this for my window, and talk about how we can get the answer from our calculator a little bit. So in my y equals, I'm going to clear out stuff from the last section, and I'm going to enter negative from the bottom row of the calculator, and then 1, x squared, because my calculator doesn't do w's for graphing, plus 400x. Again, my calculator doesn't do w's. For my window, the smallest the width can be is 0, so my x-min is going to be 0. The biggest my width can be is 400. Can't really even be 400. If I made both my widths 400, I'd use all 800 meters of fencing and I wouldn't have any length. And then the y's are my areas. The smallest my area can be is 0. And my goal is to figure out what the largest area could be, but it's going to be a big number. I'm going to say maybe 100,000, and let me graph. So each point on the graph, the x coordinates the width, the y coordinates the area. My goal is to find the maximum area, so on this picture I need to find the maximum point. If I can find the maximum point, the x coordinate of the maximum point is the width that gives the maximum area. The y coordinate of the maximum point is the maximum area. So my goal as I go through this problem for part C is I'm going to try to find the maximum point. It's actually an absolute maximum point as opposed to a local maximum point. If I can find the absolute maximum point, the x coordinate, it's going to be the width that gives the maximum area. And the y coordinate is going to be the actual maximum area. So the answer to this problem, the answer to the value of the width that gives the maximum area, this is going to be the x coordinate of the vertex of the parabola that I graphed. And the maximum area is going to be the y coordinate of the vertex of the parabola that I graphed. How do I find it? Well, in a minute, I'm going to find it by algebra. But how would I find it if I didn't have algebra nor calculus? My calculator has the ability to find this vertex. And it's kind of a tedious process, but it's a good process to be comfortable with because even my calculus students need to do it. How do I find the vertex, which the x coordinate is going to be the width that gives the maximum area, the y coordinate is going to give the maximum area. To find the vertex, I hit the second and then the trace key. So I'm going to hit the second key, which is the blue key, followed by the trace key. The vertex is a maximum point, so I'm going to pick the feature that says maximum. So second, trace, and then option 4 that says maximum. You don't ever have to do this in this chapter, but this is a nice skill to have. So I hit second, trace, and maximum, and now I'm going to hit my enter key. And after I do this, I'm going to have to trace, I'm going to have to cursor, and enter 3 times. This is the tricky part. What I've done so far is not particularly tricky. I hit second and trace, I scroll down to maximum, and now I'm hitting enter. I think my calculator is actually at the vertex, but what I need to do is I need to trace and enter 3 times. First, I'm going to use the left or the right arrow and get my cursor blinking So it's clearly to the left of the high point. So I'm tracing and entering 3 times. I'm moving the cursor into 3 different positions. The first position I move my cursor to is somewhere to the left of the vertex. It can be really close to the vertex, can be way far away from the vertex. It doesn't matter, but the first thing I need to do is get my cursor blinking to the left of the vertex, and then I hit enter. So it's telling me first trace to the left of the maximum point, and then hit enter. When I hit enter, my calculator is going to tell me where to move the cursor to. Right now, when it says left bound, it says move your cursor and get it blinking to the left, somewhere to the left of the maximum point, and then hit enter. Soon as I hit enter, the word left bound moves to right bound. That's going to be my trace and enter my second time. What my calculator is asking me to do, it's asking me to use the right arrow and trace so that the cursor that's blinking is clearly to the right of the vertex, or to the right of the maximum point. And I'm going to hit enter a second time. So first I trace to the left of the vertex. Bad visuals today. I trace to the left of the vertex and hit enter. Then I trace using the right arrow to the right of the vertex and hit enter. That's the second trace and enter. Once I do that second trace and enter, first my calculator said left bound. After I hit enter, it says right bound. When I hit enter again, as I'm going to do right now, the word right bound came to guess. And now I'm going to trace and enter a third time using the left cursor, get as close as I can to the maximum point, and hit enter a third time. And it tells me that the maximum point is the point 200, comma 40,000. The 200 is the width that optimizes the area. The 40,000 is the optimal area. So from just knowing the vertex, I could answer 2 of the 3 parts that I have left. Find the value of the width that leads to maximum area. The width that leads to the maximum area is 200, and the units are in meters. I'm going to show you in a second how to get that without my calculator. And I can answer part E. What is the maximum area? The maximum area is the y-coordinate of the vertex. The maximum area, the number is 40,000. And area always has square units. I'm going to write meters squared. And I didn't have room to write square meters, so I wrote a symbol. Done with part C, done with part E. Let me get part L. Find the value of the length. I'm just going to use this formula right here to find the length. The length is -1 times W. W is 200 plus 400. This I can do on the main screen of my calculator. Just by hit the second and quit button. It's -1 times 200 plus 400, and I get 200. This is actually a square, but a square is a type of rectangle. So my answer, the length, is also 200 meters. So I have all answers done. Let me show you how I can get the answers without my calculator. Because the graph of this area function is a parabola that opens down, I can get the x-coordinate of the parabola without graphing. And I can get the y-coordinate of the parabola without graphing. So by hand, without my calculator, to answer part C, I'm going to use the formula -b over 2a, because that is how I find an x-coordinate of a vertex given an equation for a parabola. And my a is the number in front of the squared term, which is -1. My b is the number in front of the first power term, which is 400. So to get the width that I need, I'm going to use the formula negative b over 2a, which is the formula for the x coordinate of the vertex. I'm going to plug 400 in for b. I'll get negative 400 in the numerator. And I'm going to plug 2 in for a. I'm going to get 2 times negative 1 in the denominator. This is going to give me negative 400 over negative 2. And that's going to give me the width equals positive 200 because each of the x's are widths. So I probably here should have written w equals negative b over 2a. So that's how I would get c without my calculator. I didn't use my calculator to get d. D, to get the length, I just used the formula. The length is negative 1w plus 400. And I did length is negative 1 times 200 plus 400. And got length equals to 200. And then I stole from my calculator part E, but I didn't need to. If I know a length and a width, I can use the simple version of the area formula to figure out the area. I can say the area is the length, which is 200 meters, times the width, which is 200 meters, and that's going to give me the number 40,000. Of course, I should always have units in word problems. The width was supposed to be in meters. The length was supposed to be in meters. And the area is supposed to be in square meters. So that's number 1, took 22 minutes. Let me try to do problem 2 in 8 minutes, so we get a 30-minute video. It's kind of the same question. I'm not going to pull out my calculator other than maybe to do some of the math. I'm going to do this all by hand. First, I'm going to draw a picture, and this picture is going to be a little bit different. It's a similar camp problem. A campground owner has 1,000 meters of fencing, and he's going to enclose a rectangular field bordering a river. There's no fencing allowed along the river. I'm going to let W be the width, and I'm going to try to enclose the largest rectangular region I can that maximizes area. So I'm required to use all 1,000 meters of fencing. And my goal is to enclose the maximum area. And this is a little bit different, but not terribly different. Part A wants me to write an equation for the length of a field. Ultimately, my answer to part A is going to be L equal to something. Part B wants me to write an equation for the area of the field. My answer to part B is going to be A equals to something. Let me get those, but before I get those, let me draw a picture. Didn't have a blue marker out right now. What this campground owner is doing is he's going to fence right up to a river, but no fence along the side of the river, and build 3 sides of a enclosed area, and the river is going to serve as the 4th. So I'm building 3 sides of fence with my 1,000 meters. And the way I have it drawn, I'm going to make the sides perpendicular to the rivers, my widths, my side parallel to the river, my length. And I know that if I build 1 length and 2 widths, that's required to use all 1,000 meters of fencing. So this is what the diagram is going to give me. It gives me the 3 sides that I'm building. I'm making it so that I'm building 1 length and 2 widths. You can do it so you're building 2 lengths and 1 width, but the algebra is a little messier. I'm going to solve this equation for L by minusing 2W from both sides. And when I do that, I'm going to get L equals minus 2W plus 1,000. That's going to be my answer to part A. Part B, I need to come up with an equation for an area. Well, this is a rectangle regardless of how many sides of the rectangle I'm building, and the area formula for any rectangle is length times width. That's not going to be suitable to answer any of the questions, so I'm going to substitute the answer from part A into my generic area equation to make my area equation useful to get me my answer. So I took minus 2w plus 1,000, plugged it in for L, and now I'm going to clear the parentheses by going minus 2w times w and 1,000 times w. And I'm going to get my area equation is minus 2w squared plus 1,000w. If I graphed the area equation, the x-axis would be the width, the y-axis would be the area, the negative in front of the square term would make the parabola open upside down, and the vertex is going to be the maximum point. The x-coordinate of the vertex is going to be the width that gives the maximum area. The y-coordinate of the vertex would be the maximum area. So to do part C, to find the value of the width that leads to the maximum area, I just need to find the x-coordinate of the vertex. And that's super easy to do because there's a formula for that. So the best width for this problem can be found by using the formula negative b over 2a. And in my area equation, the a is negative 2, the b is positive 1,000. So the formula negative b over 2a, I'll get negative from the formula, and then 1,000 for b, and then 2a is going to be 2 times negative 2. This is going to give me negative 1,000 over negative 4, and that's going to give me 250. So for an answer to part C, the width that I'm going to need is 250 and the units are meters. So my width that this campground owner should make is 250 meters. Done with the hard part, now it's just kind of plugging away. To get the length, that's what part D wants. I'm going to use the formula that I created in part A. It says the length is negative 2 times the width plus 1,000. My length in this case is going to be negative 2 times 250 plus 1,000. You can use a calculator and not do any of this by hand. By hand, I get 500. I'd also get that by 500 by my calculator. So the length of the field that I'm enclosing is going to be 500 meters. And this is good because you're building two widths at 250 meters each. That's 500 meters. One length at another 500 meters. So I get two of those at 500 meters. 250 plus 250 plus that 500 will be all 1,000 meters of fencing. Done with part D, on to part E. My goal is to maximize the area, and the easiest area equation to use is just length times width, because I know what the length is, it's 500 meters. I know what the width is, it's 250 meters. My area is going to have units of meters squared, and if I just do 500, can't even see my calculator, it's too early in the morning for it, times 250, my area is going to be 125,000 square meters. So the answer to part E, the area is going to be 125,000. Don't have room to write square meters, so I'm just going to do a symbol for meters squared. That's everything for 2. We're right at 30 minutes. Your problem 3 is exactly problem 2 with just the numbers changed. So you should be able to do problem 3 without doing any sort of newness. You should be able to basically just solve number 3 with the number 1400 every place where I have the number 1000, and it should solve exactly the same way. I'm going to pause and do a part 2, and we're going to do another kind of fencing problem that has costs involved.